So now I have to share my slide, right? Okay.
Yes, good afternoon, everyone. So, Dr. Pravat Jena is now currently pursuing PG program in artificial intelligence from University of Texas. Earlier, he has worked in VIT University Vellore and UPS Dehradun. Moreover, he has done his MTech from IIT Kharagpur and PhD from IIT Mandi. And also, he has been a senior fellow in IIT Bhubaneswar. So, and his major research areas include time series analysis, extreme events, climate change impact studies, machine learning techniques, data mining, etc. Regarding his research publications, he has published 9 research articles in international journals and 4 publications in conference proceedings. Also, he has completed several projects during his MTech and PhD, and he has qualified GATE twice in 2011 and 2012. So I am looking forward for his talk. And his topic of the talk is a new statistical approach to detect drought and flood years associated with weak and strong monsoon. Over to you, sir.
Okay. So thank you so much, Shivanju, and thank you so much, sir. And so my slide is visible to all of you. Okay. Okay. So good afternoon, all of you. Here, I am Pravat Kumar Jena. So this is my topic that I will be presenting: a new statistical approach to detect drought and flood years associated with weak and strong monsoon. So here, there you can find several statistical techniques to identify these extreme events such as drought and flood years. But this topic is this statistical approach. It is a conditional approach and depends on these two factors, that is strong and weak monsoons. So let's see. So outline my talk is first the motivation part. Secondly, and I have to describe the data section and their corresponding pre-processing part. And thirdly, I will discuss about that methodology. And here I have to discuss two type of method. That one is a traditional approach to detect significant periodicity, and after that, and my approach. Onwards, my approach that how to detect that extreme event along with their corresponding probabilities. And laterally, I will show several drought years and flood years in upcoming years. Then finally, that implementation part, and we'll discuss the result and discussion. Okay. So let's come to the motivation part. So how it is, how it motivates me uh, uh, to uh, to analyze the drought event and to find such statistical metrics, statistical approach to detect extreme event of our Indian monsoon rainfall. So every living with experience with majorly two climate parameters. Mainly that one is the rainfall and another you definitely that is temperature. But my work it depends on it wholly depends on rainfall. Okay, so rainfall I explicitly categorize as it is a liquid precipitation, because in climate parameter, when I said your climate parameter, then we can have that mainly temperature and precipitation. Precipitation, you will have two type. One is your liquid and another is solid part. So this rainfall is one of the liquid part of precipitation. So my work is focused on this liquid part, rainfall. Okay, so rainfall, it has a complex structure over a wide range of space and time, as you know that, because in the land area, you definitely it is very complex structure with respect to uh, altitude also, and with respect to vegetation. So again, our region, our Indian monsoon region, it experiences the tropical rainfall, or we can say that our land area, it experiences the tropical region, which is basically experiencing the seasonal phenomena, and it has high interannual variability. What it means that every years we can experience different type of rainfall amount, and this rainfall amount, it varies from year to year and also some season to season. And these two factor leads a large scale drought and a large scale flood. Okay, how it involves that I will explain laterly. But mainly these two factor involves for I'm especially seeing the large scale drought, not is a small scale, large scale drought and flood over different part of the country. So and consequently it affects the serious reduction in agriculture and vice versa to the national economics. So I like to give one of the best example. Uh, okay, so in the view of critical influence on agriculture, it is necessary to predict or forecast such variability at least in a season and in advance. Why it is required? Suppose uh, many agribusiness industry are there nowadays. So let's suppose we consider that potato chips company, and they are storing the potatoes in advance for their production. Okay, so definitely they would be interested to know that what would be the next monsoon pattern in the next season. Okay, if it is favorable, then it's okay. Or if it is not favorable for them, then definitely they will collect huge amount of potatoes in advance to in order to maintain the demand from the public. So it is one of the important point how the agri business industries are interested in climate studies. Okay, so comes to next part is our data part. So data, I have considered two kind of data set. One is observed data set, and observe, and another is model data set. Okay, so when I am saying that observed data set, that means it is a reference part that when that rainfall amount is measured through some instrument. So that rain gauge station, it is one of the example for the observed data set, and that data set can be considered as a reference one also. And this data set is can be easily obtained from IITM, Indian Institute of Tropical Meteorology, or you can or Indian Meteorological Department as well. And this data set also can be obtained from global source as well as national source. In global source, I have uh, obtained from IMD, Indian Meteorology Department, and the global there is a global source that is called CRU, Climate Research Unit. Also, it provides same observed data as well. So they have different resolution. You see, when I say that resolution, that is one depends on the time resolution and space resolution. Time means that it is a time span 1901 to 2014 provides the data in between them, and the time scale is monthly data that they provide the monthly scale. And space resolution, it is 1 degree cross 1 degree. It means that every 100 kilometer they provides one time series. Actually, every 100 square box, and if it is a box that is 1 degree to 1 degree, then and if this coordinate can be the center of this square. Okay, and when I say that coordinate, then that is only longitude and latitude. So this CRU, it provides the data every each of the square, and whereas IMD provides in two different sections. One is subdivisional data, that every subdivision they provides one time series, and that and scale is monthly. After that, also nowadays they are providing the graded data set, and it is available in 1901 to up to now. But for my study, I have used to 1901 to 2014 as well. Okay. So here, second part is climate data. What how they generate the climate data. So worldwide, there are certain climate centers are there. In that climate center, they simulate rainfall or climate variables. How they simulate it, it depends on different parameters. Suppose in the whole system, if I divide into three parts, ocean and land and atmosphere, if I divide, then there are different physical or chemical mechanism are going on, continuous process, and they generate, by considering all the variables, they generate a complex partial differential equation, and after that they solve through different numerical techniques, and finally this rainfall or any of climate data can be generated. So these climate centers are responsible for generating this kind of data set, and also they provide two kind of data. One is a historical run, another is projection run. Historical run means that they provide data from back to present status, that it is available in 1971 or to 2005. For my study purpose, I have used up to 2005, but still the data is available up to now also. And projection run, they provide from 2006 to, or maybe present time to 21st century, or maybe 23rd century at max. And the time scale is monthly. And whereas here space is non-uniform graded data, and here historical run is non-uniform graded data. Non-uniform graded data means that horizontal and vertical resolution are not same. That means they are not in the square form. Okay. So our target, one of my objectives to convert this non-uniform graded data to uniform graded data through some numerical technique. So for this purpose, I have used a bilinear interpolation. Although bilinear interpolation not so robust in this case, but among the certain interpolation technique, that binary one is one of the best one to handle this non-uniform to uniform graded data. Okay, still there is some biases are there. Some biases are introduced, but that is estimated as 15 to 20% biases are introduced. Okay. Okay, then here I see RCP 8.5. It is one of the important part of the study, because RCP is radioactive concentration pathway, that is 8.5 labeled 4.5, 6.0, and 3. It depends on that concentration of greenhouse. And if you see that this graph, I have considered the graph from Wikipedia, but it is this line. It is that the concentration is concentration of greenhouse gases rises up to 21st century. But whereas this line, suppose we consider level RCP3, it is increases up to this level, and after that it is stabilized, and it is end is opposed 2030, maybe 2030 to 40. And if you consider that RCP 4.5, then it is again it increases up to 2030 at this level. Then after that is stabilized, and also 6.0 it is also stabilized somewhere at 26, sorry, 2060 maybe. Okay, so but however, this RCP 8.5, it is that concentration is strictly increasing, and it is nowhere it is stabilized. So in order to in the view of this phenomena, I have considered 8.5 scenario, that with strict rising of greenhouse gases guesses what would be the possible scenarios of climate extremes in upcoming years. So it is one of one important target. Okay, so for the again our study area is Indian region, and here you see that this Indian region is partitioned different administrative boundaries, and these administrative boundaries are uh, mm, mm, divided by Indian Meteorological Department based on that climate patterns. Okay, and here suppose if I consider this region, and it is IMD provides a one-time series data over this region, over the large region, they provide one-time series data, but where this data is not suitable for analysis uh, for this kind of objective. Okay. But however, next our target is to convert this data, this administrative area to local administrative area. That means we have to convert this to square region. Okay, so this is done using bilinear interpolation. Okay, so here as for the data of IMD, that total subdivision is 36, but when we convert to this region to 1 cross 1 region or 1 degree to 1 degree, total I got 354 square grids. Okay, so in my study, I have considered 354 time series data to analyze this to detect drought and flood years, or as well as to detect that exactly patches where that extreme climate events have been occurred and will be occurring in future. Okay, so next methodology, as it has two parts, and I will discuss the traditional approach, and the next is what I have proposed to detect that climate extremes with the corresponding probabilities. In traditional approach, I have used discrete Fourier transform or to identify strong significant periodicity, and through that periodicity I have to extract uh, some of the climate extreme years, and then I have to apply this statistical technique. Okay, so this is my schematic of my methodology. So first of all, this methodology it comprises three parts. One is your data extraction, second is Wells technique, and last is significant test. And here first our time series is rainfall time series. And then from rainfall time series we have to extract JJs, that you know that our summer monsoon span is from June to September, so that I have extracted it from June to September time series. Then after that I normalize that data, and okay, so this is first part. But then second part, but before applying the DFT, that we have to split the data into several segments of equal length. Suppose length is let be L, and let be K segment. Okay, and when you split it, then there is possible chances that the data may be overlap. Why it is overlap? In order to avoid that uh, leakage in the signal or leakage of the data, then we intentionally keep that overlapping is allowed. So after splitting the data in different segment, then each segment we have to detrain the data. Okay, and in each part of segment, then we have to apply the undoing technique. So why again undoing technique is required? This because of the over leakage. Okay, so leakage of the signal. In order to handle that leakage of signal, that undoing technique is required to balance that leakage. Okay, so why deterrent is required? So let me explain that one first. You know the definition trend. Trend simply that it is mathematically if I say that trend is an intrinsically fitted monotonic function in which there is only one extreme. Okay, it is the best because see this is the graph, and here it is definitely this data it has positive trend. If it is positive, then how many extremes are there? Extremum is that is simply one. This point is on maximum, and here you can see that one definite one minimum is there, minimum point is there. Okay, so that is global maximum and one global minimum. Okay, so okay, how you define the D trend? So D trend within the given data span, D trend is an operation to remove the trend. Which trend? That slope. Then we have to remove the slope. Okay, question is that if we remove the slope, then what is left with us? Simply, there is only residual part is only the variability. Okay, and this variability will help us to find the intrinsic periodicity inside of data. So this variability is required to identify the periodicity. Okay, that's why this D trend is required of when we are using any time series. If it has some trend, maybe seasonal trend, because we don't need to handle the seasonal trend because we have extracted only the seasonal part. Okay, so there is no need to use the seasonal D trend. So simply we have to extract, we have to D trend the data in each part. Then in each segment, we have to implement that DFT, discrete Fourier transform, that we have to implement in each segment, and after that we have to average over k segment. Okay, so when we apply that DFT, then basically we have to calculate that magnitude of that uh, signal, because our data is in time series or time domain, and when we apply DFT, definitely time domain data will be transferred to frequency domain, and in frequency domain we have to calculate that what is the strength of that frequency, or what is the strength of that signal. Okay. Strength means that what is the amplitude of the signal. So this through that DFT we can calculate that amplitude. Okay. So this after second part, then we have to check that significance, whether that amplitude is particularly amplitude is significant or not. Okay. So for that purpose, we have to use this normalized data, and by using this normal data, we have to find that normalized power spectral density, and then up to apply this chi-square distribution for the significance. So here this chi-square distribution, it will provide a line, it will provide a curve. I'll show the graph in upcoming slide. I'll show the graph how that chi-square graph is used to identify the significant signal. Then by using this chi-square graph or that line, then we have to identify the significant peaks, and then that will be our um, periodicity. Okay, so here when I said that I have to we have to use that Wunde technique. For that purpose, I have implemented the Hamming window. Okay, so here this is formula to calculate that strength of the signal. Here this magnitude, and here this particular thing, it is converted to frequency domain, and after that we have to that it is basically it is a complex number, and after that we have to take the magnitude, that will be the uh, um, amplitude, and then after that it will average over n. Then okay, so when I have to calculate that power spectral density, yes. Okay, this one. Okay, yeah. Okay, okay. So here, when I said this normalized power spectral density, for this purpose, I have to use some classical statistical model uh, for reference. Okay, so first order autoregressive model is like this. This is the first order autoregressive model. So why I have used this first order autoregressive, because there is data is uh, it is a lag of one. The data is depends on the previous data of lag one, and so that's why it is -1, t-1, and this alpha is autocorrelation of lag one. And here this is your Gaussian white noise, and as I said, the Gaussian definitely it is a normal mean is 0 and with some standard variance. Okay, for this fast order autoregulation process, the normalized power spectral density function is here. I have not exactly derived it, but there is some derivation that from this fast order autoregulation process we can derive this uh, normalized power spectral density, and this power spectral density will um, will be used to identify that data also. Sorry, that peak also. Okay. So now for whatever we have discussed that method, the traditional method, then we have to implement it in our data. So the implementation part. Okay. See here. Okay. So this figure one. This is the result of my observed data, that my reference data. Okay. You see, this is normal. This y-axis is a normalized PhD power spectral density, and here this blue line that it is a rainfall spectrum, and this green line it is a background spectrum. So it is assumed that the rainfall spectrum should be greater than the background spectrum at least. Okay. So you see how many peaks are there. There are certain peaks. So this circle is actually little shifted to off, but my intention to highlight these peaks actually. Okay. Okay, also this peak, this one is the peak, and this peak also, and this is this, and this peak, or this one. Okay, so in first case, when this 1 2 3, these 3 peaks is not satisfying that as it is below the background spectrum, so definitely this peak cannot be considered as a significant peak, first of all. Secondly, rest peak, how many peak? 1 2 3 4 5 6 peaks are there, and that corresponding frequencies, that x-axis, it gives the corresponding frequency. But however, this frequency is not significant frequency, because my significance line is here. This is my significance line, and only one peak it crosses the significance line. So that's why the corresponding frequency, that corresponding frequency will be my significant frequency. So as once frequency is obtained, then that corresponding time periodicity will be calculated by dividing that frequency. That is 1 by frequency, which is equal to our that time period, sorry, periodicity. Okay. So here in my reference data, I found that there is 2.85 periodicity exist in my data. The 2.85 year periodicity. Okay. So this periodicity is definitely, it is more than 2 and nearly equal to 3. So that's why I have named it trilinear cycle in order to give a particular phrase word. It is trilinear cycle. Okay, same methodology is applied over 380, 354 time series, 354 time series. Same method is applied over the 354 time series, and it is found that over the 354 time series, only 191 grids, and that significant periodicity is there. Which significant periodicity? This trilinear cycle is present over 191 grids out of 354 grids. Okay. And moreover, you can see that the most of the patches are the north, and some, this is the southwest coast, and somewhere here here. But inside the central India, there is less number of significant grids are there. Okay. Then okay, so as it is definitely it is this result is a historical result. Result depends on the historical data, and same. What about the future of this trilinear cycle? Whether the future that the significance level is increases or significant level is decreases. Okay, if the significant level is decreases, the definitely that cycle may not have some impact over the different region. So here, that's why I have gone through the future data, the projection data. So I found that most of the significant grade converted to insignificance. That means that when uh, that cycle was significant at a 95 confidence level, after in future time it is found that significance level is decreased to 80, 85, 90, and in fact less than 90, in between 90 to 95. So what are the statistic of that? Statistics say that 3% of grade that significance level decreases to 80, and 25% of grade significance level is decreases to 85, and vice versa. This is 62 is for 90 confidence level, and 15 is in between 90 to 95. Okay, so here another question arises: if the significance level is decreases, then whether it induces something, it induces extreme event, extreme drought event, or maybe extreme flood event. So I am not considering flood event here right now, because significance level is decreases, then definitely it may impose drought event. So okay, so next is how to check that cyclic strength is increases in future or decreases. So why I am considering the cyclic strength? Because this periodicity 2.85, it is at a form a cycle. So that's why I am considering trilinear other cyclic strength. How it is? So first I have to calculate what is the probability that cyclic mean is less than that long-term mean. So this mean is my nothing but it is my long-term mean, or long-term mean of rainfall, and this T is nothing but my cyclic mean. So how I have to extract the cyclic mean? So cyclic mean will be extracted this using this formula, because this xi means, suppose it is a rainfall at ith year, should be greater than the rainfall of the previous year, and sorry, this the rainfall at ith year is less than the rainfall of the previous year, and also rainfall of the next year. So that means it forms a cycle. And again, this point, that rainfall at ith year should greater than the rainfall of the previous year and the rainfall of the next year. Again, it forms a cycle. So in this situation, I have to calculate the cyclic mean. Okay. So then after that, I've checked that what is the probability that cyclic mean will is less than equal to long term mean. Then I found that probability is as likely to 93.65, that your my cyclic mean is always less than, or almost always less than the long term mean. So that means that cycle in future time, the cycle of cyclic strength is reduces, and it is suggests that that significance level is decreases, again cyclic strength is decreases. That means definitely it will induce some drought in upcoming years. Okay. Okay, so in order to clearly visualize how the cycles form, here this is the one of the graph you see here. This point, this rainfall at this year is greater than the rainfall of the previous year, this year, and greater than this rainfall of this year. Okay, then definitely it forms cycle. And next is that here, this point, the rainfall at this year is less than rainfall of the previous year, and the next is also less than the next year also. So this kind of phenomena, my target to extract this kind of phenomena, and after that I have to check whether the cyclic strength is cyclic mean is less than our long-term mean. Okay. So then after that, this phenomena. So when this year, this phenomena I can term as weak monsoon year, and this phenomena I can consider strong monsoon year. Okay. So next target is when this phenomena occurs, when the strong monsoon occurs, whether it leads to drought or not. Okay. And when the weak monsoons occur, when it leads to drought or not. Okay. So if it is leads to drought, then what is the probability that that particular weak monsoon will be a drought year? And if it is a strong monsoon, then what is the probability that that particular strong monsoon will be a flood year. So for that purpose, I have proposed a methodology, and then here we will discuss what is that method exactly. Okay. So first, the first step is I have to extract that strong monsoon year and then weak monsoon year corresponding using this formula. Okay, and here R is the amount of rainfall at the ITER. Okay, after extracting this uh, data, then I have to calculate the cyclic mean. Okay, cyclic mean, and it is nothing but just average of 3 consecutive years. Okay, similarly, here I have mentioned that with respect to 3, equation 3, that means it is a this equation represents the strong monsoon, so that's why it is a cyclic mean of strong monsoon. Okay. Similarly, I have to calculate the cyclic mean of the weak monsoon. Okay. So after calculating this one, then I have to extract the cyclic mean from the from Ri. That means the year which satisfied the equation 3, the year which satisfied the strong monsoon, from that year I have to extract that cyclic mean of strong monsoon. Again, the year which satisfied that weak monsoon, I have to subtract the cyclic mean of weak monsoon. Okay. From this data, definitely one can say that it definitely will follow the skewed distribution, because one will be right skewed, another will be left skewed. Okay. Okay. So from here, this X, it follows right skewed distribution, where Y is likely to follow left skewed distribution. And also from visualization, it is already clear that X will follow right and Y will follow the left skewed distribution. But however, if you calculate some statistic, then definitely you can apply the case test, and from case test you can conclude that X and Y time series will follow right and left respectively. And what is the statistic value? Statistic is 0.002. That means we are pretty much sure that these two data time series will follow the right and left distribution respectively. So for such kind of data, definitely we cannot apply the normal distribution technique to check whether which point is lies in the critical region or which point is lies in the main region. Okay, but as it is skewed, we cannot apply that. So for that purpose, we can use the skewed Gaussian kernel distribution, which is a mixture of the skewed heavy-tailed or light-tailed distribution, to estimate the density function of the time series X and Y. Okay. So for that, kernel density function is like this. I have used this kernel density function, where K is nothing but our Gaussian kernel, and H is the bandwidth, and N is here a number of data point, and here this Xi is our time series. Which time series? This X and Y, this time series. So after calculating this density of X and Y, then I have to extract the flood year and drought year. Okay, so flood year will be here. Xi is, if Xi is greater than d of alpha. What is the d of alpha? D of alpha is nothing but it is my threshold to identify which one will be flood year and which one will be the drought year. So again, this d alpha will be calculated from another technique. That technique is bootstrap technique, and then I will explain what is the bootstrap technique here. Okay. After that, again, once this year is extracted, then I have to calculate what is the corresponding probability, and that probability will be used by using that kernel density function and using this threshold also. Okay, so this PI probability of a particular ith year would be flood year if then corresponding probability with this one. This will provide that corresponding probability. Okay. Similarly, for flood year, oh sorry, this is drought and this is flood. Okay. So if probability yi is greater than d of alpha, this provides that corresponding probability that particular year will be drought year. Okay. So our next target is I have to calculate what is the d alpha first. Okay. So d alpha will be calculated by using the bootstrap technique. It is a for this purpose we have to use some um, oh sorry, yeah. I have used some inbuilt function which is in R. R is a statistical time series analysis tool. So in this R, you can have a function that is boot is inbuilt function in which it will take three arguments. One is your data, D is your data, and then there is a function boot function that it is a customized function. You can customize it, or you can change as your choice. You can modify it. Okay, so I have modified based on my choice, and n boot mean how many number of times I have to run my code. Okay, this function, how many times I have to run this function. So here boost function, I have used in this particular case, I have used the median because you know that when the data is skewed data, so mean is not suitable to use for the purpose. So instead of that, we can use the median. So I have just changed little bit in this boot function. I have used the median. Okay, so median of how many median we have calculate? We have to calculate n boot number of median we have to calculate, and in my case, this n boot is equal to 4,000. So it is a huge number also because again it is suggested to keep on run this function in the large number when your distribution to converge. Until your distribution is not converged, then you have to run this file or run this code. Okay, once your distribution is converged, then you have to stop it. Okay, so that number should be noted, that how many time after how many times that your distribution is converged to a particular number. Okay, particular number, particular interval. So in this in my case it is 4,000. After 4,000, that particular interval is converged. So okay, so uh, how many n boots, how many medians I have calculated? I have calculated n boot number of times, that is 4,000. Okay. So that is each median will be arranged in a particular ordering, that then that m1 to up to n boots. Okay, so by using this ordering, I have to calculate 2.5 or 97.5 percentile value, and this value will be my 95 confidence uh, 95 confidence interval. Okay, so once confidence interval is obtained, then I can easily find that what will be my d alpha. So it will note that ci of median is interpreted as 95 of the time the population median lies in the ci boundaries. Okay, it is definitely just oriented to all. Okay, so how this interval is median, confidence interval of median is calculated by, it is calculated by using this formula, 0.05 divided by 2 into n boot number of times, and lastly this once k is calculated, then this k will be subtracted from n boot. So that index, this value will provide your upper bound of the interval, and this will be the lower bound of interval. Okay, so result in when we convert this time series, then it looks like this. So here, this is the result of my observed data, and this is of my observed data as well. If you remember, when I subtracted that so that cyclic mean of weak monsoon, then you have to provide the skew distribution, and it is a left skew distribution, and it is when I subtracted that cyclic mean of strong monsoon, then it provides a right skew distribution. This is the density function. It looks like this. Okay. And what will be the critical region here? My critical region, based on my threshold, this is my threshold. So my region is, this is my critical region, and within this region, that all the year can be considered as drought year, and in this year, and this is my d alpha point. This boundary is my d alpha point, and this is my critical region for to find that flood year. Okay, so all the years belong to this region is my the flood year, and all the region of this lies in this region will be considered as a drought year. Okay, So, okay, so here, as for the observed data, it is found that the weak monsoon to cause drought at 95 confidence uh, level is found to be 0.29. It means 30% chances that weak monsoon cause the drought, and there is 39%, almost 40% chances of that strong monsoon cause that flood years. Okay, so this result is of my observed data by reference data. Again, this analysis is again done through climate data as well. And what is the climate data? As I discussed, the climate data two part. One is historical and is projection. Based on the historical climate model, I have considered four model here. Here one is, this is the name of the model, one model, and second, oh, it is not E, it is ES. Okay, and this is third one and fourth one. Okay, oh, sorry. It is correct actually. This is for weak monsoon. This is for strong monsoon. Same data model data, and this is for weak monsoon, and this is for strong monsoon. So based on this model data, it is found that 28% chances that weak monsoon caused the drought year, and that 31% chance that strong monsoon caused the flood years. Okay, so it is almost equal. That drought result is almost equal with our reference result. But however, this data varies little bit, because in our case it is 40%, but model says it is only 30% chances that strong monsoon caused the flood years. Okay, so this is your historical. This result is based on historical data. Next is uh, next is projection. So again, this projection, it says, so it is overlapped again. In projection, see, projection that says that weak monsoon cause, sorry, 36% chances that weak monsoon cause the drought. However, only 27% chances that strong monsoon cause the flood. So in future, that there is chance that that drought event will be increased, and there is chance that flood event will be decreased based on this result, and the result is confident at 95 confidence level. Okay. After that, some particular yeah, local region is identified, and also some drought event over the decade. Suppose we consider to 20 to 29, 2020 to 29, these regions will be experiencing, or is likely to experience the drought event, and these regions will likely to experience that event over the time domain 30 to 39, and 50 to 59. This region would like to experience the drought event. So again, similarly, next is I have calculated for the flood also, and these regions are likely to experience the flood event over this region. Okay. So this result is based on these two models actually, but however, there are the 29 climate models are there, and there is high chance that the result may vary from model to model. Okay, but uh, yeah, maybe there is a high chance that the result may be overlapped in some cases. Okay, yeah. So this is all about, and this is my reference, and thank you. So Mm, yes. Hmm. Okay, okay, yeah. Uh, all right, sir. I have collected the data from government agency that Indian Meteorological Department provides this data, and also Indian Institute of Meteorological Department also provides the data. First of all, and second, suppose when you if you have to collect from global source, then there is a open source that is here, Climate Research Unit. It is in UK, and they also provide that same kind of data with more accuracy actually, and also their data spread over the every corner of the Indian land region. But however, IMD provide data, but if you can might experience with some data will be missing in some hilly region, like maybe extreme region of Himalaya region, that some data may be missing. But however, CRU data provides every corner of the globe, and you can get that data clearly. Okay, so I have collected from 1901 to 2014 during my PhD time. So I have collected to 14 to 16, I think, 2016. And that climate data, climate model provides from 1901 to 2028 also, and also future data they provide that 2020, 22, 21st century. And also that data is also freely available by using some first we have to create a login, then they will validate that page, then after that they will provide the link, and from that link we can download the data, so that climate model data. So uh, yeah, but that climate model data is as I said that they generate through different complex process. So that's why that data, before using that data, we have to apply some statistical technique to bias to validate that data set. Huh. Okay. Huh. Yeah, actually, yeah. So, see, as I said, the rainfall is a very complex process. So it depends on that monsoon, and depends on that region, whether that region is complex terrain region or not. So as our analysis to suggest some particular area that where it likely to experience that flood year, or maybe flood event, or maybe drought event. Uh, but and if you consider only very local region, in particular Assam, then different different other climate variables should be considered in order to analyze that one. So there are some regional climate models are there, and in that model we have to use some physical parameter as well. There are several physical parameters that models are there. Then I have to do parameterization. Then we have to predict whether that this year will be event flood event for this particular region or not. Okay. So and that can be obtained real time, but it will be a very complex thing because we have to consider so many climate parameters as well. Yeah, definitely it will be complex. But IMD is doing right now that they have proposed a model, and they have started. They have working on. They are working on it because they are forecasting that cyclone. So they definitely they can forecast that flood event easily. But that is going on, and definitely they will do. Yeah. Thank you so much.